Bismillahirrahmanirrahim. Assalamualaikum and a very good day to you all. In today's video, we're going to continue about steady state conditions in self-contained bearings from the Shigley Mechanical Engineering Design book. Okay, so case in when which lubricant carries away all of the enthalpy. In case where lubricant carries away all the enthalpy, increase when the general bushing pair have been already been discussed. Okay, bearing in which the warm lubricant stays within the lubricant housing will now be addressed. This bearing is called self-contained bearing because lubricant sum is within the bearing housing and lubricant is cooled within the housing. These bearings are described as pillow bomb or pedestal bearing. Okay, they find use on fans, blowers, pumps, and motors. For example, integral to design consideration for this bearing is dissipating heat from the bearing housing to the surrounding is the same rate as enthalpy being generated within the fluid film. Okay, so what does it mean by this slide? Means that in the previous slide we had discussed when fluid coming from the left, okay, coming from the left, going up on the uh, outside, okay, left going up to the right. Okay, this is what you have discussed before. What about bearing that cannot go anywhere? It is within the region only, like your aircon. Okay, like lubricant in your air conditioning. Okay, it doesn't go anywhere. So how do we calculate it? Okay, so self-contained bearing, the sum can be positioned as a keyway, like cavity in the bushing, the ends of the cavity not penetrating the end planes of the bushing. Film oil exits the annulus about one half of the relative peripheral speeds of the journal and bushing and slowly tumbles the sum lubricant mixing with the sum contents. Since the film of the top half of the cap has cavitated, it contributes essentially nothing to the support of the load, but it does contribute friction. Bearing caps are in use in which the keyway sum is expanded peripherally to encompass the top half of the bearing. This reduces friction for the same load, but the included angle D of the bearing has been reduced to 180 degrees. Charts for this case will include in Remini and Boyd paper. Okay, you can read it. Okay, this is the heat given up by bearing housing. May estimate from equation. Heat loss, H loss. Okay, heat loss equals to HER A TB minus T infinity, which is H, H loss is heat dissipated in BTU per H, British thermal unit. Okay, per hour. HER combined overall coefficient of radiation and convection heat transfer. Okay, A is the surface area of bearing housing. TB is temperature of bearing housing, surface temperature of housing, and T is the ambient temperature. Okay, so this is the equation that we will use throughout the subject. Okay, the overall coefficient HCR depends on material, surface coating, geometry, the roughness, the temperature difference between housing and surrounding object, and air velocity. After clearance and others in ordinary industrial barometers, the overall coefficient HCR can be treated as constant. Some representative values are this value for still air, for shaft still air, for air moving at 500 feet per minute. Okay, and 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 an expression similar to figure 1217 can be written for the temperature difference TF minus TB, which is TF minus the bushing temperature within the lubricant film and the housing surface. It is impossible because the bushing and housing are metal and very nearly isothermal. If one defines TF as the average film temperature halfway between the lubricant inlet temperature TS and outlet temperature TS, okay, inlet temperature meaning that when the fluid coming into the bearing. Okay, and then the following proportionally has been observed between TF minus TB and the difference between housing temperature and ambient temperature, TB, minus infinity, minus T infinity, which is minus ambient temperature. Okay, TF, this you can see, and alpha is the constant depending on lubricant scheme and bearing housing geometry. You will see the alpha value in the next slide. Equation A may be used to estimate the bearing and housing temperature, and table 12 to provide some guidance concerning the suitable value of alpha. The work of Garellis allows the broadening of application of charts of Raymond D and beyond. If you remember the previous video, 1 hour video talking a lot about this chart. Okay, uh, okay, to apply to variety of bearings beyond the natural circulation below block bearing. Okay, so this is the lubricant system, the alpha, the value of alpha condition for moving air, 1 until 2, still air, half until 1, oil bath, moving air, half until 1, still air, at least 1 over 5 to 2 over 5. This is the range of alpha. Okay. And then solving equation A for temperature of bushing and substituting in equation 1217, give the bearing heat loss to the surrounding as this equation 1219A, and writing equation A, you get this equation, temperature of bushing equals to TF plus alpha, ambient temperature 1 plus alpha, which is alpha you can see in the previous slide. Okay. In beginning, a steady state analysis and the average filling temperature is unknown. Okay. Hence, the viscosity of lubricant is self-contained bearing is unknown. Finding the equilibrium temperature is an iterative process wherein in trial average film temperature and corresponding viscosity is used compared to heat generation rate, okay, and heat loss rate. Adjustment is made to bring these two heat rates into agreement. This can be done on paper with tabular array with help of TF to achieve the equality between heat generation and heat loss. A root finding algorithm can be used, even a simple one can be programmed for a digital computer. Okay, because it's the same like previous video, the lengthy video, 1 hour video on Remedy and Biot graph. Okay, uh, you you want to find a suitable temperature in it is an iterative process, meaning that many try and error and using your experience also. Okay, in practice you should ask your senior, technician, senior engineer, what is the temperature. If your product is the new product, then you have to do try and error many time. So until you get the suitable temperature for your lubricant, for your inlet lubricant. Okay, because when you will know, that along the way, along the process, the temperature will rise, and then the viscosity of the liquid may become lower gradually over time. So what is the suitable viscosity for that lubricant? It is an trial process. Okay. Because of sharing action, there is a uniformity distributed energy release in lubricant, and heat that hits the lubricant is way around the bearing. The temperature is uniform in the radial direction, but increase from the sum temperature Ts by an amount of uh, difference of T during the lubricant pass. The exiting lubricant mixed with the sum content being cooled to some temperature. The lubricant in the sum is cool because the bushing and housing metal are nearly uniform lower temperature because of heat losses by convection and radiation to the surrounding at ambient temperature. In usual configurations such as bearing, the bushing and housing metal temperature is approximately midway between the average filling temperature, okay, and the ambient temperature. The heat generation rate, okay, at steady state is equal to the work rate from frictional torque. Expressing this in BTU-H, British Thermal Unit per hour, requires conversion constant to 2545 BTU per hour and 1050 uh, this lubricant pound per inch results. in heat generation is 2545 Tn over 1050. Okay, this is the equation. For it, you can see the equation is 95.69 U and power of 2 LR3 per C. Equating this, you can solve for TF, give TF equal to this equation. You remember T is the revolution general speed, the general speed. L is the length of the general. R is the radius. R is the radius. Uh, ACR is the head loss, okay, and AC is the area of the bushing, meaning that hand, if my hand, my finger here is the bushing, this is the area, not here, not here, not at here, not at here, but is the area of the bushing. If my hand is the bushing, this is the area, okay, and C is the clearance. Okay, so example 12.5, this is the picture is the pillow box bearings. Okay, for those who are not familiar, this is the picture of pillow box bearing with a keyway sum. If you're familiar, I'm sure you're familiar with the diagram for general bearing. Most of our equation concerning of general bearing and the earlier illustration for general bearing is come from this kind of bearing. Okay, if you remember some of the equation, some of the hydrodynamic theory and everything, it it resembles this pillow box bearing. Okay, you can see in the previous videos. Okay, in the earlier video. Okay, consider a pillow box bearing with a keyway sum whose journal rotates at 900 revolution per minute in sharp stirred air at 70 Fahrenheit with alpha equals to 1. Lateral area of the bearing is 40 inches square and lubricant of SAE grade 20 oil. Gravity radial load is 100 pound and L per D ratio is unity. Okay, meaning that it is so long. It is so long. Okay, L, this is length, this is radius, L over radius ratio is there are four options. One, L over D is 1, L over D is 1 over 4, L over D is 1 over 2, and L over D is unity, meaning that it is so long. Okay, the lubricant has general diameter to 2 plus plus minus 0 and negative 2, and bushing bore, you can read it. And for minimum clearance assembly, estimate the steady state temperature as well as minimum film thickness and coefficient of friction. Okay, how to do this question? They want us to find the steady state temperature as well as minimum film thickness and coefficient of friction. Okay, so the minimum radial clearance, C min is, you can see here minus, and you can see the equation, and you can get 0.001. P from this, trace back the value 100 where it come, 2 where that is come, 2 where does it come, and everything. And the famous Sommerfeld number, never forget Sommerfeld number, because you will use it throughout this chapter. If you mistake, you do mistake, one mistake, everything will be mistaken. Don't do mistake. Okay, and then the viscosity is microrand, horsepower is found as follow, has power, okay, you can get uh, this horsepower. Okay, the friction of power loss. Okay, heat generation rate with British thermal unit per hour is heat generation. From this equation you can get 3.637. Okay, and equation 12.9 12.19a, you can get this equation from alpha given in the question and everything. You can get 0.35. Build a table for trial value. Okay, meaning you have to build a table like this. The solution needs you to build a table. For this, you put all the value, you get the value, you get this. And then the temperature in which H generated and H loss equals to 46.3. You can get from figure 12.24. Okay, and all of this you can get TB equal to this. Okay, S equal to 0.65 minimum clearance, and coefficient of operation. This is the minimum film thickness, 0.0079 from figure 1216. Remember the last previous video, we do a lot, very lengthy video on minimum film thickness. The same graph you will use. Okay, the same graph you will use, figure 1216. Okay, and coefficient of friction from figure 1218. Remember the same graph. Okay, from the previous video. This is the equation, and parasitic frictional force is this equation. Okay, I advise you, uh, bring when you study this equation, because it involve many graph. Have the textbook with you, beside you. Okay, have the textbook beside you. Okay, because you have to refer to the graph. Okay, so that's all for this video. We see you in the next video on clearance. Thank you very much.